All right, let's go ahead and get started. So it's my pleasure to introduce our CRB seminar speaker series today, Professor Marc Miskin. Marc is assistant professor of electrical and systems engineering at UPenn. Before that, he was a postdoc at Cornell, working with Paul McEwen and Itai Cohen. And before that, he got his PhD at the University of Chicago. Marc has received many prestigious awards, such as the Packard and Sloan Fellowships, Army Research Young Investigator Award, and Air Force Office of Scientific Research Young Investigator Award. His research has been looking at designing and fabricating and building microscale robots manufacturers using microfabrication techniques. The aspect of Marc's work that I'm really excited about is, unlike most or nearly all microscopic robots, his robots are fully autonomous with full control loop of sense, compute, and actuate, fully on board and embodied in the robot. So Marc, I look forward to hearing about your work. Everyone, please join me. Welcome, Marc.
Thank you. And it's just you're welcome to interrupt me throughout the talk if you guys have questions as we go. So this is going to be the tiny robots talk. And basically the way I understand myself is I am the tiny robots person. I like building small machines. And if you're wondering what I mean by tiny, that should be illustrated, I think, by this image up here. So here's two of the robots that we built in our group. And the thing you're hanging out right here is a cross-section of skin. It's actually a sample that we took from a high school microscope slide kit. And each of these little tiny things coming out here, this is where a hair follicle would grow. This top layer over here, that's the upper part of your skin, the dermis on the outside. And each one of our robots sits about here. So when I say tiny robots, I mean really tiny robots. I mean microscopically tiny. That everything you're going to see is literally a robot that is too small to see by eye. But our goal in talking about these is figuring out how we retain all the properties of big robots, right? How do we keep them being smart? How do we keep them able to sense? How do we keep them able to obviously move, right? And building all those things in this package that's still really, really small. Now, obviously, that's a huge challenge. But there's a reason to be optimistic. And it's sort of the inspiration, I think, of why we do everything that we do. And it's basically nature, right? Is that the fact that we put this image on here is to remind us that everything in biology is basically made by little tiny machines. And even if you take a single microorganism, it's still remarkable in terms of the complexity that you can achieve at these scales. So this is one of my favorite microorganisms. This is what's called a rotifer. These little guys live everywhere on Earth. They live in salt water, fresh water. If you were to go take pretty much any sample of water, you'll probably find some of these guys hanging out. And they're called rotifers because of this cool thing that they're doing right now. So this one has got these little hairs on the front of its head that it moves. It almost looks like it's wheels spinning, but it's not. They're actually hairs pulling stuff in. And what it's trying to do is suck up these bacteria that are hanging out in front of it. It's hunting. It wants to eat. I remember seeing this thing when I was a kid, probably about like 8 years old, under a microscope. Is one of the first things I ever saw, and it totally blew me away. And still as an adult, I still think this is absolutely amazing, right? In order to hunt, in order to be hungry, in order to find food, to communicate, this thing has to be smart. It has to be able to sense its world, make decisions, carry out actions. But it does all of that in a space that's under a hair's width in size, right? Nature basically shows you very clearly that there's no reason you can't build something that's very small and yet very complicated. It's really an engineering challenge. It's how do we humans figure out how to do it for ourselves, right? How do we, okay, birds fly? How do we make planes? It's the same idea. This thing exists. How do we do it with our own tools to where we know how it works? And obviously, I'm not the only person that's into this idea of trying to build tiny machines. But when you look at what people have built to try to emulate nature, you see an impressive body of work of all kinds of different devices that move and operate at small scales. But in some sense, they're kind of more like motors than they are like robots, right? So here's some examples of things that you'd see in kind of the traditional microrobotics literature. So these are little tiny particles that are, if you shoot them with ultrasound, they'll propel around. These are little bubble rockets. They're basically layers of different metals that when you put them in peroxide, make little bubbles behind them, pushes the thing around. Kind of a canonical microrobot of a helical corkscrew that's got a magnet on one side. You put it in a magnetic field and the thing turns, and then you can make it swim and you can guide it by changing the magnetic field direction. People are super desperate to make things move. So this is basically a sperm cell that swims into a magnetic harness, and then you can guide that thing around. And all of these things obviously move and they have some level of control, right? You can tell the sperm where to go, or you can guide this magnetically, you can guide the ultrasound to move this. But in some sense, they're not exactly robots because they're tied to something big and external, right? They lack the capacity to have onboard computation. And so to me, that's very different than that microorganism, right? Nobody tells the rotifer where to go. The rotifer knows where to go, right? It does it on its own. It has some ability to compute. And so the question I want to ask is, why is it so hard to make these things smart? And you might say, well, that's because they're small, right? It must be difficult to build things that are small and have computing. But that's not really true either. So this is the world record. If you were to ask what's the tiniest computer anybody's ever made, and this record was set in 2017, so you could actually do a lot better if you were to make something more modern. This thing was made by folks at the University of Michigan, by David Blau's group, who's an expert in small scale computing. And this thing next to it is a grain of rice, right? So this is a remarkably tiny computer. It's about 1/3 of a millimeter on the side. And you may wonder, like, okay, well, how is this a computer? Well, it's a computer. It has memory, it has RAM on it, it has a little tiny processor. It's got a communication system in the form of a little solar cell and a little LED that lets you send data down to it and it can send data back. It has a power supply in the form of little solar cells, and it even has some sensors, right? So this one I think was designed to measure pressure, but you can also measure temperature, you can measure electric fields, all kinds of stuff. Now, if you're a roboticist, if you're a micro-roboticist, this is awesome, right? These are all of the parts that you would want to build a robot, right? Memory, processing, sensing, communication, power, all in a package that's really, really small. And it maybe shouldn't come as too much as a surprise, because if you've been keeping track of the volume of computing systems, they've been miniaturizing forever. But there's a graph, canonical description, this is what's called Bell's law, basically states that the volume of computing systems has been decreasing with an exponential trend since the 60s. And if you trace this out, it does a pretty good job of predicting trends that we've actually seen, right? So you get laptops show up in 2000s, 2010, you get smartphones. And right about now in 2020s, this would be when you go sub 1 millimeter, when you can finally build computing systems that are under the characteristic length scale that we would consider macroscopic.
Dr. Miskin, it stopped sharing your screen. Can you share
Really?
your screen?
Oh, boo. So what are they saying? Just no,
They're just seeing the owl.
the owl? Oh, weird. It says I'm sharing the screen. Okay, let's try again. For the virtual people. Yeah. Somebody else says they see the screen. Of course. Presumably back.
Better.
Okay, good. Okay, so right. So the point is that this is one example of many. There are now a growing number of platforms of computing systems that are below 1 millimeter in their characteristic size. So what's the challenge, right? And to me, the challenge is basically this, right? Because if you want to build a robot, you need to basically build the two parts together. You need to figure out how to build a computing system to have your intelligent systems for your robot, your sensing, your computing, your decision making. But you also need a body. You need something that's going to move this thing around. And basically what we know how to do well in the clean room is we can build bodies for you that don't have brains, or we can build brains for you that don't have bodies. But how do you do both together, right? And that's mostly what my group does, is we try to address how do you fuse these things? How do you fuse them together to build a robot? So I'm going to tell you a couple stories today on how we did that, a few different versions of robots that we've been able to build that featured both electronics and mechanical systems in them. And then I'm going to spend a little bit of time telling you about what they're for, right? What we're actually going to use these robots for in the long run. So the first system we built, though, is to try and address this, is this little actuator that you see up here. And this is a bending actuator that we designed specifically for building electronically controllable micro robots. So it's a bending actuator, so what that means is it curls up into this kind of helical shape, and then you can uncurl it the other way. And this big black thing here, this is a probe that we use to apply voltages to this actuator to trigger it to move. Now, this thing may not look like much, but we're super excited in this movie. I actually did this when I was a postdoc, and you can see it's kind of bending erratically. That's because it finally works. And I'm pushing the buttons, and it's working, and it's amazing. And that's because it's real small. So if we were to put a red blood cell up on the screen, this actuator would be about that big. Now, similarly, in addition to this being small, this thing has some other remarkable properties that stem from the way that it's made. So what is this? Well, it's a device that we call a surface electrochemical actuator. And what it is it's a super thin layer of platinum. So here's the platinum, stacked with a little tiny layer of titanium on top. This is what you'd see if you were building one of these things. So we build them on top of little layers of aluminum that we used to pick them up. And this is the actuator sitting on top. And you can see the scale bar. This is 10 nanometers. So this is just a couple dozen atoms or so thick. Now, it turns out that if you take platinum and you put a voltage on it while it's in water, atoms from the water will attach themselves to the surface of the platinum or remove themselves depending on the amount of voltage that you use. When you do that, you create a difference in stress because you're changing the number of bonds on this surface, and that stress can be used to drive bending. Now, why does this work? Well, because this thing is just a couple atoms thick. So adding one extra layer of atoms, it really cares. The thing's going to bend like crazy. Now, why do this electrochemically? Well, one very nice thing about electrochemical processes is they have a very characteristic voltage scale of about 200 millivolts. That's the exact same voltage scale that you would see in a semiconductor piece of electronics. It's the same amount of voltage it takes to drive a transistor all the way from on to off. It's actually for the same reason. They're both thermally driven processes. And so if you plot, how much does your actuator bend as a function of the applied voltage you find, you can basically go rails to rails over this very, very, very tiny voltage range. Last, you can do some more measurements. You find out the force these things output is about a nanonewton, which I know in your world doesn't sound like a lot, but to me that's huge. A nanonewton is like if you build a robot that's enough force to where a 100 micron robot could carry 50 times its weight, like an ant, right? Like it's super big. And likewise, the power is about 10 nanowatts. You probably don't need me to tell you that's super small, right? So this is a very nice actuator if you want to build a micro robot. You have high deformation, you have low voltage operating, high force, and very low power. There's one other key property, and that's that platinum and titanium are both commonly used materials in clean rooms, and so that means you can make a bajillion of them. In the same way that you use semiconductor techniques to build circuits, you can just turn around and use them to build your actuators. And so here you have, whatever this is, like a couple million little actuators waving at you like the legs of your future robot army. This is great if you've had a bad day, you have very low self-esteem, you can go down in the lab and inflate your ego until you remember that you work in the basement. So we're excited. We've got our actuators. We're on our way. And so we decided to build something very simple. And so this was our first sort of proof of concept robot. And really the goal here was to show that these two things actually play nice. So one thing to say you can get semiconductor electronics to interact with an actuator. It's another thing to actually do it, right? You have to show that the processes in the clean room aren't going to destroy each other. And so we built a really simple design with about the dumbest circuit we could build. It's just two little solar cells, but they're made out of silicon. And we wired them to sets of those legs, these special C's legs that we made with our new actuator. And to turn that bending pattern into something that looks more like a robot, we basically patterned big rigid blocks of polymer on top so that you would localize bending and make these into little hinges, sort of an origami inspired robot. Now, because we built the circuits in the clean room with standard sort of CMOS semiconductor processing, we built the legs with standard CMOS semiconductor processing, we could build the robots with standard semiconductor processing. So much like a circuit board, you can build a full 4-inch wafer. Actually, I have the chip today, cool. Here's one of those chips. That's 10,000 robots on that guy. But we build them typically on a disk about the size of your hand, which you can pack 1 million robots on. And much like circuits, complexity in this process is basically free. So if you want to make every single robot different, you can do that. If you want to make every single robot the same, you can do that. The only limit is the smallest feature you want to build, but it's a totally parallel process. It's completely irrelevant how many you want to pack in here. So you can see in this design, we have about 4 different geometries. Currently, our group probably does about 16 to 20 in a given fabrication, which is kind of cool. Now, the last thing we had to figure out in getting this whole thing to work was how do you go from these things, which are glued down on a chip, to robots, right? If we were building circuits, we'd be done. We'd just wire up bond pads and then, go give this and put it in your cell phone. But a robot's got to do more than that. It's got to be able to walk around. And you can see in this image, these are not going to walk around. They're glued down on the thing that they were built on. So the last thing that we had to invest a lot of effort in was figuring out strategies to get these off of the wafer and into the world at large. I'm not going to bore you with it because it's super boring and really technical, but I will say our group is really good at it. So this is what it looks like if you watch the last stages, right? So here what we're doing is we're using chemicals to dissolve out the surface underneath each of these robots. And you can see when we finally clear the material underneath, snap, their little legs fold up. And now you have your little robot army. You've actually got 10,000 little robots hanging out. We're pretty good at this. So in this video, we're getting about 90% yield. We have processes now where we get up to 99, which is pretty awesome. If you're a first year grad student, it's maybe 50%, but if you're fourth year, you do awesome, which is really very cool. It means that you can build, if you say you're going to build 10,000 robots, you can build 10,000 robots on the other side. Again, because you're building with this very parallel technology. Now this is all well and good, but you may wonder, do these things actually work? And of course they do right here. So let me show you. So here's one of our little tiny robots. And if you look up here, you can see there's this little white dot. That's a laser spot that we can control. So basically we have a series of little mirrors that can move this laser around under computer control in this microscope's field of view. And what we're going to do is move the dot back and forth between the solar cells that drive the front of the robot's legs and the solar cells that drive the back of the robot's legs. And off this thing goes, just sort of shuffling around in its little tiny micro world. You can play fun games, build all kinds of little robots and shuffle them around. This is my favorite movie that we made from this generation because you can see this stuff diffusing around randomly. The particle's actually small enough that it's being kicked by the water molecules and diffusing brownie in motion. And here's our robot, just maybe a few factors of 10 bigger than that little tiny particle moving out in this environment. And so this was the last thing I did as a postdoc before I became a professor. I thought this was the coolest thing in the world, going to work every day and zapping microrobots with lasers. What more could you possibly ask for in your life? And so the very first thing I did as a professor was to completely remove the laser, was to take that joy away from my students and make it something much, much cooler. So this work got picked up by this guy, Michael Reynolds, who was a postdoc at Cornell and was a postdoc in my group. And the first thing Michael did was get rid of the laser system, which was really just proof of concept anyway, and replace it with some onboard circuits. And so Michael designed these little tiny circuits in 180 nanometer CMOS that we sent to a foundry in Germany. We sent it to X-FAB. And basically, it's got another solar cell that supplies power, but otherwise the solar cell turns on a little tiny clock that produces a gate cycle for the robot. And the gate cycles you hard code onto the device by deciding where you wire to that clock. You just get little terminals that would select phase differences. And so we made little quadrupeds, we made little bipeds, and we made what is my favorite robot in this work, Antbot, which is a 6-legged robot that does the canonical alternating tripod gate. Now, from a robotics point of view, you might say, okay, alternating tripod gate, beyond, but dude, it's 100 microns. It's a super, super tiny robot. And what's also very cool about this robot is it's running on daylight, right? That we didn't do, there's no crazy power budget here. You can take this robot outside, it's engineered to run at basically 1 sun of power, and it'll wake up, go through its thing, doesn't need you to tell it anything else to do. All right, so this was sort of the state of the art of things in 2022, where we demonstrated this new approach to building microrobots where you could integrate electronics. And what kind of our group has been doing since then is really trying to explore this world, right? We view this very much as a platform technology that's going to let us do all kinds of really, really cool stuff at this length scale. And so some of the things that we've been exploring in the new world of electronically integrated microrobots, I'm going to tell you about these 3. I'm going to tell you about a story of making other microrobots electronic, making smarter circuits for a robot, so going beyond clocks. The title of the talk should tell you we go further. And then taking the fantastic voyage, so actually using these robots for something. And I'm sure everyone thinks we use them for biomedicine. We do. The one other thing I will say is, if you are interested in making tiny sensors and tiny actuators, that's something else we do. So, much like this projector has little tiny MEMS mirrors flicking back and forth, there's lots of cool stuff you can do just with parts that move and just with parts that sense. So some other small fraction of my lab is also into like, okay, we solved all these problems to build this thing. What other technologies can we deploy? And if you're into that space, you should ask me. But for today, just going to tell you stories. And we're going to start with this one. So how do we make other microrobots electronic? Okay, so that goes. This story kind of goes back to this slide. And when I started at Penn, I had to teach a class like everybody else does. And I created a class for my graduate students. I'm teaching about microrobots. And so you can't teach a class where every lecture is I'm the best and everyone else is bad, right? That would be kind of a terrible course. And so you have to learn about all these other platforms and really think about like, well, what are they good at? And one of the things that struck me is that a lot of these platforms, even though they're not smart, are actually still pretty cool. They have a lot of really nice features. Like, take this thing. It's not electronically controlled, but it's really robust, right? And it can swim at super high speeds, right? Or this thing can go deep in the body because of these magnetic fields. And so we got curious, right? Like, are these really just precluded from having electronic control, or is it just no one's done it, right? And I'm increasingly of the opinion that no one has done it, right? That in a lot of these cases, they're actually very straightforward paths to implementing electronic control, which perhaps isn't surprising because electricity is probably the easiest form of energy to convert between different domains. So if the propulsion mechanism for this is chemistry, figure out how to convert electricity into chemistry. The propulsion mechanism for this is magnetic fields, tie electricity to magnetic fields. And so the first robot that we built in this vein was we basically said, could we take one of these other propulsion systems and bring it within this family of now electronic control? And we honed in on this one here. So one way that you can make something that moves that's very, very small is to take a particle, say this is a particle, pretend it's not a robot, and to place it in an electric field. If you do that and you're in water, you'll get electrophoresis, right? You'll get that the object will move in proportion to the magnitude of that electric field. It's how we separate DNA strands. It's how we move colloids around. basically there's little charges everywhere on the surface of this particle, usually because it's glass and it's a chemical process. And when you put the electric field on, you get forces in the fluid from those charges, and that can lead to propulsion. Now, there's loads of micromotors in the microrobot world that work this way, but what nobody seems to have pointed out is that there's no rule that says that the electric field has to come from chemicals. It doesn't have to come from anything external. It could come from you. It could come from electronics. And so we had a very simple idea. Let's make this field by using electronics on the device. So what we did is we again took some onboard solar cells and we wired them to 2 metal electrodes. And if you do that, you're going to get a plus over here and a minus over there, and then that's going to create a field in the environment around you. And so in principle, that should lead to propulsion. And yes, it does. Right? You can now have something that swims. And so this thing moves like any other self-propelled microparticle using electrophoresis, but now it's generating it with a circuit on its own device. And we did some work to characterize this. So we found, some very simple trends like the speed of the robot is proportional to the current you supply because it's proportional to the electric field. It's inversely proportional to the conductivity of the environment because it's proportional to the electric field. And if you plot it as electric field, you get a straight line because it's proportional to the electric field. Well, what's cool is that if you play with this in different chemical environments, you always find the same trend. You always find that the speed is proportional to the electric field. Now, different chemical environments, you get different proportionality constants, but the general structure of the equation is the same. But note the magnitudes of the different proportionality constants that you get for all the different chemical environments you could try. And we put this thing in whatever we could find in the lab. So we put it in like peroxide, we put it in DI, we put it in acid, we put it in formaldehyde, everything anyone's built a micromotor in, we put the robot in and we saw what it does. They only differ in mobility by maybe a factor of 3 or 4. But the speed you can control with the electronics, you get 3 orders of magnitude. So what that means is by making this one simple change, by going from a particle that normally would passively swim to one that you control electronically, you can now build something that will robustly operate in different environments because you can simply dial up the amount of current you apply in order to overcome chemical changes. We did some work to characterize this device as well. I don't want to go too far into the detail, but it's kind of an interesting fluid dynamics problem. So here's one of these little devices swimming around. You can see it has 2 engines. And basically, when you dial up the power and the current going to this thing, you can see it actually sort of scoots around on a layer of fluid underneath it. Basically, the way to think about this is it's kind of a self-driving air hockey table, right? That little layer of fluid is propping the thing up to hold it above the ground because it has mass. And you can work out from this, from the fluid mechanics in this problem, what sort of the angle of attack will be and the gap height will be as a function of the applied electric field. And so we did some modeling and we can roughly predict the angles of attack that we see, and we can predict the gap heights that we see. I'll say the data here is wide because these are really hard experiments to do, but this model only has 1 free parameter in it. So we're pretty confident that the fit is actually quite good. Okay, so what can you do with this? Well, let's say you now have this device where I've got 2 of these engines and I glue them together, one on this side and one on that side. Now I know that regardless of the chemical environment I'm in, each of those engines is going to try to move at a velocity that's proportional to the applied current going through it. And so if I were to think of this as a robotics problem, the natural mapping would be this is wheels, right? I have 2 sets of wheels, and this one wants to go at one speed that I can control by applying the current, and I could go at another speed I can go by applying the current. And once you know that, you know everything there is to know about this problem. This is robotics 101, right? This is the first thing you ever do. And so you say, okay, I know the radius of turning for this is going to be proportional to difference these currents, and then I can just apply macro scale control laws to pilot this thing around. And so this is a closed loop system that we're running where we're doing this with a basically camera watching this robot and then modulating the laser power being delivered to each of these engines to, in this case, I think, do a proportional control scheme. You can also do bang bang with this. You could pick your favorite robotics controller and implement it to pilot this robot around different waypoints. Because it's optical, you can play fun games with multiplexing it, so you can get a swarm of these robots. Here we have 3, and we're telling them to fly in formation, doing little waypoints in sequence as they move together. Again, all this is running through some robot overlord watching these things, telling them where to go. Or you can make little tiny robot conga lines if you're my graduate student and you want to make little tiny robot conga lines. So basically, Will is piloting this robot, telling it where to go, and these other robots are chasing after whoever they've been assigned in front of them. Again, doing this all through closed loop feedback. So kind of cool. And what does this get you? Well, again, like if you're to think of the classic sort of micro swimmer, they're usually hard to control. They're hard to independently control. They're hard to have multiple of them moving in the field of view. And again, just simply by adding electronics, you can map this into a canonical robotics problem where now you can port everything you know from the macro world down to small sizes. Yes.
How do you give differences to fields?
What's that?
How do you have to
This is all through light still, right? So this is a really simple design with just solar cells. And so basically all we're doing is patterning light. And you know, it sounds really hard where it's like, well, how do you pattern tiny light? And it's like, we're really good at patterning light, right? You just take a projector and you focus it in the back of the microscope, or like use a laser. This one's actually done by, if you're curious, we did do some hard work here. So this is a holographic laser projection system. And the reason we designed it that way is that basically you can scale to large numbers of robots because the power distributed to each of the robots is essentially a fixed fraction relative to there's no wasted power. So whoever you're trying to activate, you deliberately deliver it. So you just buy a huge laser that has a ton of optical power, and then you dial down its power for the number of robots you want. But you can scale like 10,000 robots with this if you wanted to. Now, there's a problem with this design, right? And that's that these robots are still dumb, right? And so presumably, hopefully someone in the audience is wondering, what about this? You promised this, you promised we were going to have computers, and now we have conga lines. Like where, why, when does this happen? And of course, the answer is this happens now, right? So the second story I want to tell you today is, okay, cool. You could take other microrobots and make them intelligent, but you can do a lot more if you build circuits, right? And I think, by the way, these are related goals. Like if anything you now make electronically controllable benefits by winning in this space. The circuits don't care what the actuator are. They'll port, right? The challenge now is how do you start making these things smart? And so we got into this maybe 5 years ago. And this has been a very, very fun project, but the driving person who's helped out with a lot of this has been my collaborator, David Blau, who is the person who made that little tiny computer on the other side. And so basically when David came out with that little tiny computer next to the grain of rice, we called him up and we said, hey, you know, we build small robots and would you want to make a robot with us? And he was super excited. He said, yeah, totally, let's do that. And so this is the design that we've come up with now after a few years of iteration. We condescendingly refer to it as SmartBot. I know that's a common name in robotics. We mean it as a joke. But this is kind of our little tiny robot that we have. And again, this device is super small. So it's about 210 microns by 335 microns. So about 2.5 hairs widths on that side, something like that. But in that space, we're able to pack a whole bunch of stuff. So again, this thing's powered by solar cells. And we designed this robot to, again, run on daylight. Actually, the total energy consumption of this robot's about 100 nanowatts, which means pound for pound, it burns about the same amount of energy as a paramecium, which is about the same size. It's kind of cool, in my opinion. It's got a set of sensors on it. So there's now thermometers on either side of this robot. And you can both measure the temperature and then store it to memory. And you can also measure differential measurements and say, okay, is the left half hotter than the right half? There's a series of voltmeters. This robot's designed to live in water. And so you can measure the electrical potential in the world around you. Same rules, you could do magnitude or you could measure differential. There's a special communication suite, a little solar cell down here, and then some electronics that accompany it that allow you to send instructions to this robot, basically by modulating the intensity of the light around it. There are specialized electrodes and drive circuits underneath them. So these are little pads with clock circuits underneath. Basically, this robot supports both actuator classes we've developed, both the electrokinetic propulsion mode and the legged robot mode. And underneath here are essentially control circuits that you can tune the polarity, frequency, or phase for the pad on top. So if you're the legged robot, you can pick a gate pattern by picking frequencies and phase. If you're the electrokinetic robot, you can set polarities. It's essentially like having wheels that you can swivel and change the directions of. You can change your thrust vector. And then all this in through here, this giant pattern of wiring, it's a processor with about 4 kilobits of memory. So this robot has a custom instruction set architecture processor on it. It's an 11-bit system, and we have special instructions we wrote for this robot to compress it. So you can give it lines like measure your environment as an instruction or travel for as far as instruction, but it also supports canonical sort of, computer architecture instructions. So you can do adding, you can do if statements, branch conditionals, all the kinds of stuff you'd want to have in a program, all packed into here. In the real world, this device looks like this. So in the bottom there is Maya, who's my graduate student who worked on this. She's kind of the real hero in getting this to work. And you can see it, hanging out in the 0 of a 2020 coin. All right, so let's say you have one of these and you want to play with it. Here's what you do. You turn on the light and the robot boots up into a default mode. So it actually has a bootloader, which is kind of cool. It loads its own instruction set into its system. And then you program it by, like I said, flashing intensity pulses in the microscope field of view. So these robots, you don't have to localize. It's a purely global communication modality. You just flash light at it. It decides what it's going to do, but it won't respond to anything. You have to send it a passcode first. So you have to first send it an 8-bit code that says, hey, I'm now talking to you. You need to listen to what follows. And if it sees the correct code, it loads the remaining flashes into its memory register as a program it's going to do. Every robot knows 2 codes, which is kind of cool. They know global code, which is universal to all microrobots we build. And then they also have specific names, right? So you can say, hey, robot 5, this is your instruction. Robot 10, that's your instruction. Again, without having to localize them. And then, when you're done, you send your execute command and off they go. Now, these robots have no permanent non-volatile memory. So if you want to reboot them, you just turn the light off and you go back into the default state. We did a lot of work to automate this process to make it like a real robot. So there's actually a compiler that you can pick your instructions of what you want this thing to do. You hit run, it'll convert it into assembly for the processor and then build the optical flashes that go downstream of it. All this now happens on a PCB, which is pretty cool. So you don't have to have any knowledge about how our robot actually works. We can give you the PCB, we can give you the code. And then if you've got a modulatable light source, which typically you have if you have a microscope, you can start programming your robots to carry out tasks. This is a demo we did a while ago where we're basically telling the robot to lift its different legs. It doesn't have legs, we're probing it directly electronically, but you can see it carries out the correct actions on the other side. It raises its foot, puts its other foot down. Now, let's say you build one of these, and the one we're going to talk about today is the electrokinetically propelled version. So again, this is the same idea as that robot that we were moving around with the laser light, but now we're going to do it all on robot. So I've got 4 electrodes for this robot, and each of these I can independently set the polarity of by giving instructions through the microcontroller. So if you have 4 electrodes and 2 polarity states, you have 14 distinct configurations for this robot. So there'd be 16 total states, but 2 are all high, all low. Those don't do anything. And so we went through them. We characterized what this thing does. So you wind up with some nice behaviors. So you have a forward drive mode where you set 2 in the front high, 2 in the low, back low, off you go forward. You can do sliding motion. So you can set the lateral directions high and low, and you'll translate on the orthogonal axis. You can do 3 low and 1 high, and you get what we call an arcing behavior, which is basically a turn with a forward motion. And you can also do any 3 low and 1 high, and you get a turning behavior, where you get a nice little pivot in place behavior. From a robotics perspective, this is nice, right? You have complete control over all your degrees of freedom in a fully digital signal. Right? It's just 1s and 0s, and then you know what the thing does. And so then you can stitch things together and say, okay, here's a program. I want you to run forward for a period of time, rotate by 90 degrees, slide along the axis, and then turn. And then off goes your little robot, running forward for a period of time, turning by 90 degrees, or chasing it on the microscope, and then sliding over in the direction on the other side. All of this now happening autonomously on the robot. We're giving it no instructions. So we've satisfied the first goal of any robotics project of making your robot do a cool dance. Purely an open loop. But so then we said, okay, this is pretty cool. Let's start getting the sensors in here, right? This is a program that we're giving this robot, but we built this thing to do closed loop behavior. So let's see what we can make it do. And so the first thing we wanted to do is validate that the sensors work at all, right? No one's ever built one of these before. We wanted to make sure it's correct. And so we wrote a very, very simple program, the bare minimum for sort of a sense, think, act, but that we would be able to independently verify that the robot is actually doing the right thing. So a very simple task. So the program is this. Basically, the robot is going to run around for a period of time, make a measurement of the temperature in its environment, digitize that measurement, and then send the data back to you by doing a little dance, where each step, whether it goes forwards or backwards, encodes a 0 or a 1 with the Manchester encoding. And so here's our little robot over on the left, hanging out. There it is sending you zeros. That's a 0 being sent over to you. And you can run this, right? You can say, I can go and work out like what I can build a chart that lets me determine what temperatures correspond to what measurements it makes, right? So these are register values from the sensor versus temperature, and there's nice linearity between the two. And then you can decode the displacements of the robot's body to decode, okay, it's sending a 0, 0, 0, 0, 0, 0, 1, and then you look up what that temperature is, and you find out, okay, it's 15.6 degrees C. So now you say, okay, I've got a procedure where it makes a measurement and then tells me what it saw. I can validate that by measuring the temperature independently and making sure the robot's doing the right thing. So we did a very simple experiment where we put the robot in a bath that we cooled down by putting it in a fridge. We put it under the microscope. We independently measure the temperature of the bath with just a thermocouple, and then you measure what the robot reports back. And you get basically these 2 traces where the robot is the open circles, the probe at the closed circles, and you get very nice agreement over about 120 minutes where the robot is digitally communicating this data back to you. If you're not a micro person, this may seem kind of dumb, but if you're a micro person, this is awesome. So measuring small temperatures, like we get about a 0.1 C resolution at 100 micron spatial resolution is real hard. That's actually really quite difficult. And so we were pretty impressed with this, and we're probably going to pursue this independently as a sensor. But today we're going to be roboticists, and we're going to say this is super cool. What this really does is it validates that our sensors work. Let's move on to doing something of a more interesting behavior. And so this is where we got to, and there's currently experiments that are running nonstop in our lab to elaborate on this, but I'll show you sort of the maximum extent of our now almost published work, where we implemented sort of an actual behavior where you're using feedback from your environment. So here we wrote a very simple program where we could independently verify the behavior, where the robot has two states where it can either spin in place or it can execute that arcing motion to go explore space. And whether it transitions between one of those two states depends on whether the temperature it has just measured is higher or lower than the previous value. So essentially, it's a very crude mechanism for doing thermotaxis. And I sit there, and if the temperature is the same as I saw before, I just keep spinning. If it has suddenly gone, I think it's programmed in this case to go down, down, then I'm going to start arcing until I find somewhere cold, and then I'll go back to spinning on the other side. Now, why do we pick these? Again, this is really easy to verify. It's easy to tell whether something is spinning or place or traveling off in some direction. And so it's a clean signal. And what we're going to do is we're going to program this robot to do it. And then we're going to turn on a cooler underneath it. So it should initialize by spinning in place. And then when we activate the cooler, the robot should go off trying to find a new environment until it does, right? So here's what you get. You turn on your little robot. It correctly boots up and starts spinning in place. Cool, just doing its thing. And then your graduate student turns on whatever the cooler underneath it goes, it's cold, and then off it goes running around. And so we had to chase this thing, which unfortunately makes this movie hard to interpret because both the robot is moving and we're moving simultaneously. But when you deconvolve the data, you get graphs that look like this, which are excellent. So here's our robot. It starts out, it's turning in place. You turn on the heater, off it goes arcing, trying to find somewhere new to go until it makes it, this zone is cooled, this zone is not cooled. So it makes it into this region where it correctly determines, oh, okay, finally I found somewhere that's back to my normal temperature and I'm happy. Just to be good scientists, we flipped the gradient of the temperature by putting another heater under here that we then turned on. And you can see the robot responds to that new heater being turned on by again going into an arcing state, although its radius of curvature now is a little too big, never quite makes it over to the other side and just travels off to the corner of the microscope stage where it dies. If you get deep in the data, you find out that it actually is doing exactly what it's supposed to, where basically the curvature of what the robot is up to is a good proxy for whether or not you're in the arc state or the spin state. So you go from high curvature, basically no curvature. At the same time, you go from not translating to translating, and they correlate to when we flip the heater signals from one side to the other. So we're super happy about this. What's going on in our lab right now is we're developing more exciting versions of this. So we sort of have a bang bang controller version of it that we built. We have a couple other control laws for this that are more elaborate kind of Markov chain models that make this thing function. And I think we'll have more to say about this in the near future, but it's actually pretty cool. So you can climb gradients and all kinds of other stuff. So where do we go from here, right? And I'll say that getting this on this robot's memory just barely comes close to saturating the memory capacity for this machine, which may make you a little bit worried. But I have reason that you should be hopeful as well, right? So the first thing that's coming soon that we're going to be able to well, we know we can do, and we're going to build more on in the future, is everything I've shown you so far were instruction sets given to one specific robot. But we do know that we can give specific instructions to specific robots as well. So in this movie, we're instructing the one robot on the left to run forward and then rotate, and then the second we'll tell the one on the right to start rotating as well. So one of the mechanisms we're going to start building out more is utilizing this passcode mechanism of identity for robots in order to give specific instructions to specific members of a given robot swarm. And this, would probably not be super useful if the robots all they could do was swim around and do thermotaxis. But we're also executing a new tape out this month. So we're pushing our process technology down by another factor of 10 in terms of the size of the features that we're building. And we're pretty confident the next robots we're going to have in about a quarter, so about 3 or 4 months, are going to have about 100 times more memory. They have a module now for local robot to communication that we're going to build, a 10x enhancement in speed, which is also going to be cool. And one other fun feature, which I have not told you about, which is the capacity to grow metal on their bodies when placed in the appropriate solution. So a new module we've been working out are ways that robots can grow metallic fronts that can bond together and assemble into macro scale structures. All of this to me is super exciting. And I think if you're into robots that work together to build things that can execute different commands, that can communicate, that can sense their environment and do it in closed loop, I'm very optimistic about this, right? I think this is going to be a very cool direction for all of this technology in the very near future. Okay. So I think I have what, like 5 minutes left? So I think we're like right on time, which is good. Awesome. So I have one last story to tell you, which is our story of, okay, what are they for, right? So we can build a super cool robotics test platform where we can do closed loop control and memory and sensing. And you know, by the way, these robots are also super cheap. So we're happy to give them to you if you want them. We don't care. We're going to kill them all anyway. So we're happy to share. But you know, besides building structures and working together as swarms, what are they actually for? And the place kind of everyone I think implicitly assumes they're for is biomedical applications, right? You have a tiny robot. What do you care about that's that important and small? And the answer is parts of your body, right? That when you have problems at this length scale, it often leads to disease. Virtually every time I give this talk, somebody asks me if I've seen this movie. The answer is yes, I've seen this movie. Don't ask me. But if you have seen this movie, or whether you haven't, right, this sort of Fantastic Voyage, it's a movie from the 60s where they shrink down a submarine and it goes inside of a scientist to like remove a blood clot. One of the things that this movie does well is it justifies why you would ever want something small to go in a body, right? Like most of the things, like medical technology is pretty good. And in a lot of cases, you can usually work your way around it without necessitating a micro robot or a micro submarine. But there are cases where you really desperately want that technological capability. And so one of the questions that our group asks is like, when do you really need a micro robot for precision medicine? Like when do you really have to justify like it being mechanical, it being able to move, it having some degree of like sensory feedback or whatever, and that you couldn't just do it with drugs or surgical intervention? Like why do you really need this machine? And we have a couple different ideas in this space, but probably the most exciting is this story that we've been working on for a little bit, and I'll show you some preliminary results. Bear in mind, this is going to take us like 20 years to figure out, but I think it's a cool project. And it's a story on peripheral nerve repair. So when I started at Penn, I was grappling with this question of like, why do we actually need these robots in medicine? So I gave a talk at the medical school. And one of the people in the audience is my now collaborator, Casey Cullen, who pointed out this really cool problem that we've been working on since. And so what Casey told me is that if you were to look in the surgical space in peripheral nerve surgery, it's kind of grim. So peripheral nerves, right, are the nerves that wire your brain to the rest of your body. And in the US, there's about 100,000 of these injuries every year, right? Where you have kitchen accident, car accident, you sever a nerve, you lose sensory or motor function. And in spite of that huge number, about half of those injuries have no positive outcomes, even with surgical intervention. So you go to the hospital, they say, okay, we're going to do the surgery, and 50% of the time, absolutely nothing happens at all. And then the other 50% of the time, usually the outcome is kind of blunted, that it's not really full sensory recovery on the other side. Now, I always thought that that's because nerves don't regrow, but that's actually not true. They do regrow. And what most surgical interventions try to do is they try to show the nerve the right place to grow back to, right? It's a little tube, the surgeon implants it, the nerve tries to grow down the tube and get back to the muscle it's supposed to be connected to. But the problem with that is that the nerve grows at a very fixed rate. And so if it doesn't make it back to the muscle it's supposed to be connected to within a time frame of about a month, then the muscle dies, and then there's no chance of ever recovering from that injury. And so you can work it out. You say, okay, there's this time scale the muscle is going to die. It's about 3 months, and there's a rate that the nerves grow, which we don't accelerate. There's a critical distance of about a centimeter or so. It's about 2 centimeters roughly, where if the nerve injury is shorter than that, you're on one side of that 50% curve. If the distance from where it's supposed to be to where it was cut is longer than that, you're out of luck. And so what you'd like to be able to do is to make these nerves grow faster, right? That would be the key thing we'd actually like to accomplish. But none of our technologies are able to do that. Now, I got to the end of the talk, Casey pointed out that these two images of this bundle of nerves and this microrobot are to scale, that they're almost exactly the same size. And what's remarkable is that the force you need to make one of these things grow faster by pulling on it is almost exactly the force that this robot outputs on the other side. So one of the things you could do is you could exploit the fact that nerves have a little bit of elasticity in them. If you tug on them, you can make them grow faster and get this robot to pull those nerves. So for 5 years now, we've been working on this to build microrobots that need to pull nerves literally where they want to go. It's a crazy idea, but if you think about it, it certainly justifies why you need a robot, right? It's an inherently mechanical process you're trying to do. And you can't do this with drugs. There's no way of making nerves grow faster, and you need precision. You have to grab the right thing to pull on. You grab on the wrong nerve, you don't want to do that. This has been a nightmare, getting robots to play nice with cells, as you might imagine. This is what usually happens. So you get your bundle of nerves, you put them in with your robots, and they grab your robots and they toss your robots around because they're cells and they're really, really strong. And so this is an experiment we did where we co-cultured a bunch of nerve cells. These are basically those nerve fibers that we're going to try to pull. And here are our robots where you can see when the nerve reaches them, it latches on and throws the robot around. And if you wait long enough, you get images like this, where your robot is now completely encased in neurons. Oh no, where's my thing? Okay, so where are we? What have we been able to do? Unfortunately, we can't quite tow them. It turns out that this one little robot got stuck, but we're very excited about this project for a few reasons. One is this is the first robot that's been able to operate with cells around it for a month, right? Which is super cool. So a lot of the processes we've developed in this have allowed us to actually get into the space where we can plausibly do medicine. The other thing is, if you watch this movie closely, you can see there's this little tiny bit of stuff on that robot's, bad robot. It's this little tiny bit of stuff on the front of the robot being pulled back and forth. That's one of those bundles, and we are deforming it, right? So we've got enough force, we've got enough lifetime to the robot, and the reason this robot doesn't work is because we're bad roboticists. We haven't actually engineered its legs properly to walk on this medium. And so I'm very optimistic that this is something we're going to be able to do, hopefully in the near future, and have these little devices where if we just get a little bit, would you believe it? No one studied the problem of locomoting through axon bundles. So this is something we're gonna have to figure out. And it turns out just grabbing the design you know how to build is not the way forward. But we got a lot of beautiful data from this, and we're looking forward to now engineering this thing to walk properly in this environment. The good news is the force works out, the lifetime works out, and so I think we're actually gonna be able to pull this off. All right, so this is my last slide, and this is kind of my story for everybody in the room as to what I think is kind of the broad vision of why I think this is super cool. And I have this statement at the bottom, which is quasi-provocative, but I really do believe it. And it says, we're entering the age where the micro world is no longer the privileged domain of biology. And I'm saying that to you, partly wearing my robo hat and partly wearing my nano hat, right? That if you were a nano person and you built small things 20 years ago and you looked under a microscope and something was moving, it was alive, it was a cell, right? It was probably something that was active and biological. But in the last 20 years, we've gotten so good now at building systems, at building parts, at building devices, that we're finally in a range where we can build things that aren't nearly as sophisticated as biology, but can at least emulate some of their functionality. And I think this is just a super exciting time to work in this space, that you're going from simple machines now to systems, right? And that opens all kinds of new doors. The flip side, of course, is that even with those simple functionalities, you can begin to address really incredible problems that would have otherwise required mastery over the biological world, which is hard, right? So I'm very excited about this prospect, and I'm looking forward to maybe coming back in 10 more years when we've got even more to say about this space. So that's my talk, and thank you for your attention.
10 minutes for questions.
Yes. Sure.
I studied neuroscience. I'm not familiar with the electro stuff, but I'm really curious about just like the one that you showed, just like to recover stuff. But based what I have known, just like really basically from neuroscience, just like the neuron, just like they communicate with electricity. That's the robot, micro robot, just like disturb because the the power is actually just like similar to the neuron where they just like firing each other. Is the electro field is gonna disturb the neuron communication?
We haven't seen any. Yes, that's a really good question. So basically what you're saying is while you're driving these electrochemical actuators, you're modulating the charge density of ions, and so you're kind of like a neuron depolarizing.
Yeah.
I don't think we've seen any evidence of that, probably because they're decorrelated, right? That there's no, and our drive frequency is much slower than the typical pulse frequencies in neurons. But there are cases where neurons have really, really slow pulse frequencies. Like it's possible you could build things where the neuron correlates with the robot. Kind of one of the goals in the stretch growth project is actually to pull the axon out and then do to study it, right? To see if it's viable, to see what its electrical properties are. And hopefully we'll have more to say on that when we've done that. But as of right now, we're still at 0th order, right? We're just trying not to kill them. So that's kind of, we'll worry about whether they merge with the robot later. But right now, the hard part is making sure that they're just, robot not get killed by cells, cell not get killed by robots. That's a great point. Yeah. Yeah.
I see that all your experiments where the robot is sort of active or have electronics on them, the power is coming from solar cells,
Mhm.
which is not available usually inside it, right?
So there's two comments there.
Can you
So,
repeat that question?
so the question is, you know, it's coming, all the robots in this work are solar powered, which is correct. And that, that's not available in vivo applications. Yeah, so there's sort of two answers to that. The first is, we only like solar cells, but we don't have to use solar cells, right? We're electronic. So, anything that you can use for power transfer to small systems, you can use in this approach. So for example, we have a project that we're trying to start up where we're basically stealing from the implantable electronics community to do power transfer with magnetic fields. And we don't care, right? Our actuators just require voltage, the electronics just require voltage and current. I couldn't care less where it comes from. Just give me 100 nanowatts of power, that's all I want. That said, light isn't as bad as you maybe think, right? So if you take a laser pointer, shine it on your finger, you see the dot on the other side. Light is limited by scattering in the body, and so if you're just using it for power, it's actually not that bad. You can get to about a centimeter into the body. While, you know, you're not gonna be able to do comms because the light scatters in every direction, but you can get enough power intensity in NIR to operate at about 1 centimeter in depth. And for the stretch growth application, most nerve injuries are like kitchen accidents, which are about 1 centimeter in depth. So at least that one, like, you'd probably be able to handle most of the use case, even with optical power. But if, you know, but we couldn't care less. Like, if we want to do it with acoustic tomorrow, fine. The only issue is it makes the fabrication a little bit harder because now you got to build circuits, legs, and a power transfer system. Whereas if you use the PVs, you're going to build the circuits anyway, so you got those for free, right? And that's kind of why we lean that way.
Another question, Paul, have you ever planned to, like, you built like 1 million robots, right? And usually in robotics, when we talk about million robots, we talk about one. So, and that requires like communication between robots. And I see that's on your slide, but can you elaborate a bit more?
Sure. Yeah. So basically, the proposed communication module is to, just had to change it. The flashing was bothering me. The proposed communication module is basically to drive electrical currents in the solution around you and then measure them with the voltmeters on the robot. And so the design is you basically have a 4 kilohertz carrier wave on each of the robots. And then you can modulate that carrier wave to transmit data. And then there's also each of the robots can do frequency shifting so that they can talk in independent channels. And so it's kind of a nice one for robotics because you can work out like what your range of communication is. You can build it so it's about a body length, and like if you get near my range, I can talk to you and we can transmit data. So that's the design. It'll be on the next tape out, and it's very tailored towards swarm stuff. One of the other things too, which is going to be cool in that design, is that you can transmit as part of that signal the ID of the robot you'd like to have that message. So you can use the passcode and say like, hey, I'm talking to you. Which robot are you? Oh, you're that one? Cool. Here's what I want you to do. So we're really trying to design it towards swarms, right? And I think, by the way, if anyone has input on what would be really cool to add on that robot, we're all ears, right? If you have some really cool algorithm that you're interested in that requires X functionality, it might be too hard, but if it's not, we'll add it, right? That'd be something we'd like to build. Yeah.
Might be like forward on the stretch code project, but with the like robots that you deploy, kind of given like, you know, you want to pull their bundles together and make the connections, but if they are successful in doing that, then like what's the next step for the robot? Because either it kind of gets mummified in your nerves or it gets out. But like,
Yeah.
how does that work?
So the kind of first indicator application is you would use it to augment current surgical interventions. So the way they do it now, right, is the surgeon implants this tube and the tube does nothing to accelerate growth. It has attractants to try to pull the axon in there, but that's all it does. So kind of the first clinical indicator is you put the robot in the tube prior to implantation. The robot binds to the axon, marches down the tube to accelerate the growth, and then the surgeon's got to remove the tube anyway, right? And so that would be part of that where you'd presumably, you know, we don't know, right? Because no one's ever removed a microrobot from an axon. But the original proposal was that you would remove the robot in addition to the tube, and then you'd basically re-damage that axon, but the distance it has to travel now is much shorter. So that was kind of the original version, is there would be a separate surgical intervention step that would then remove the guidance conduit and the robot. And basically what you're doing then is re-damaging the axon, but now you just have to go this little tiny 100 micron gap, so the probability of success is higher. Long term, right, you could envision like designing schemes where the binding mechanism degrades. So like we currently functionalize them to get the thing to bond in the first place. And you could build things where like, that's an unstable bonding mechanism, and then over the lifetime of the towing, it comes off. That's gonna take us a while, right? That's a hard thing to figure out, and so we're targeting kind of the dumber goal first. But if you had to pivot, if you're gonna say like in 20 years, like I want it to go the length of my arm, right? That'd be the way to do it, is you'd make it so it degrades over time. And then surgically removed.
Is it possible to like find a way to just like dissolve it?
So there's a whole school of thought in microrobotics for bioresorbable microbots, right? So like Brad Nelson's like super in this space. And you can do that, right? You can build things where like your system dissolves over time. And there's even limited capability in electronics, right? Where you can build some electronic systems that dissolve over time. You're probably not going to get like this, right? This is probably way too sophisticated for any of that. But if you could boil it down just to the mechanics problem and maybe some very limited control, then yeah, sure, like that would totally be another route. I tend to think like, I think there are different schools of thought, right? It's like, do you want to be more like a device and like a surgery, or do you want to be more like a drug, right? And in my mind, I favor the surgery side because the object I'm building is already inherently mechanical. And so most of the tasks I'm doing are similar to surgical tasks in the first place. But there is something to be said for like the just have it dissolve, right? That's a very powerful concept. But it's a different school of thought, and you know, I like electronics and I'm not willing to give it up yet. Yeah.
How do you grab on to the axon, and then is your goal to just pick out specific fibers, or just kind of like attached, like you're in a tube and you're trying to attach to all of them, or like what?
So it's like the 0th order goal is like, if you look at this image, this is a bundle. So these are a whole collection of axons, and you kind of at this scale, just grab a bunch and march, right? And hope that you get the right thing in the right spot. There is a really cool piece of biology that was sort of one of the things that we talked about when we designed this project, which we think is doable, but it's probably too hard for us in the near term, which is that if you actually do get a nerve injury, your body tries to guide this process naturally. So one of the things that happens is the nerve dies downstream of the injury, like the distance between like where it's cut and where the muscle is, all the nerve dies. And the insulating cells that normally wrap the nerves, they're called Schwann cells, reconfigure into a tube on their own, which is meant to guide the axon back to where it's supposed to go. So it's called the bands of Bungner, right? It's this really weird phenomenology where like the white blood cells go in and clear out all the dead axon, and then they sense there's no more electrical pulses going down them, so they reconfigure into this tube. And so kind of the dream of this would be like, if you could build the robot small enough, it could go down that tube. And then you could just dump a bunch of them in and then have them carry out that task and just pull the whole band back in parallel. It's a super hard goal. We'd have to downscale our robot by about a factor of 10. But, you know, if we get better at it, then I think, you know, something I'd like to pursue, I think it'd be really cool. So for now, the idea is basically we're clunky and we're going to do this the way surgeons do. We get a big tube, grab a whole bunch of axons, hopefully we get the right one there. And the goal we're just trying to meet is accelerate the process, right? We're going to be as sloppy as the current interventions are, but at least we're making it grow faster, which will help get that 50% up to 60%, right? And that's a big deal, right? That's like 10,000, 20,000 people a year. Could you do it better? Absolutely. And there's all kinds of really, really cool things here, but
How do you actually grab onto the axon? Is that like
you
a-
don't. So the way you do it is you treat the robot in proteins that make the axon want to bond to it and adhere to it.
Okay.
So basically and that was part of getting this thing to work. So I hid something from you, and that's that this robot, even though it looks like the robot I showed you in the beginning, or here's one that's really covered in crap, and you can see it's trying to stretch this axon. Actually, this one's funny because it's been wired backwards. So this one's a bad robot because the grad student wired it the wrong way. But you can see this is partially transparent, whereas the platinum ones weren't. So we actually developed a new actuator for this around an electroactive polymer called P.PSS. And one of the reasons we had to do that was basically to make it function and survive the functionalization step, and to boost the force output to be able to do this pulling mechanism. So I also sort of hid that detail, like there was the reason we're not stretch grading them is because we dumped a bunch of time into engineering them for this task. So we reworked all the actuators, we reworked all the electronics for it. We basically built these functionalization schemes, and you can see you do it right and it's nice and sticky, and this thing's going to be on there all day. Yeah. There is an interesting question though too, like if you get it close enough to the muscle site, there's, you know, in biology, the axon will actually preferentially debond and go over to other stuff. We don't know if that'll happen, but it'd be cool if it does. So we'll find out.
All right, so I think we're out of time. Thanks again, Mark.
Yep.